Welcome to the course on power quality. We are discussing the numerical examples on series active filter. Coming to example number 11, a 3-phase series active filter of voltage source converter with AC series inductor, coupling transformer and its DC bus connected to the battery functioning as a load is used in series with the 3-phase AC supply of 440 volt 50 hertz, feeding a 3-phase diode bridge rectifier used for charging a battery of 580 volt at 60 ampere average current to reduce the harmonics in AC mains current and to maintain almost unity power factor as shown in figure. Calculate A, the line voltage at the input of diode rectifier, B, AC line current, C, RMS current of active power filter, D, RMS voltage across the series active filter, and the VA rating of series active filter. Well, this is the system that we have a typically a voltage fed load. After diode rectifier, we have a typically a battery charging load, and this is the series active filter by which we are injecting the voltage in series with the line, and the DC link of series active filter is connected across the battery of the load. And the very purpose of series active filter here, of course, by appropriately injecting a suitable voltage, we have to maintain this supply current well sinusoidal balance and in phase with the supply voltage, so that the unity power factor operation is achieved. Well, after keeping all the parameters with the developed model, this total system is simulated, and these are the simulated performance. The supply voltage, which is balanced 3-phase voltage. This is the voltage what we are doing, since we are injecting a voltage in such a manner that current is sinusoidal. So, we are forcing the diode to conduct 180 degree and virtually charging this battery with all the 3 phases simultaneously, and well, the battery voltage gets reflected at the point of common coupling, and the voltage at the PCC comes in this shape. This is similar to the waveform what we get by 3-phase inverter switching with 180 degree waveform. So, similar waveform is here for phase voltage, and this is typically the supply current which is in phase with the supply voltage. So, thus the power factor at supply is unity, and this is certainly the current at PCC, since the circuit is series circuit. So, both current are the same, and this is the voltage which is injected by series active filter in series with the line, and if we inject this voltage, which is a difference of this voltage and this voltage, then we are able to force all the 3 diodes, all the 3 phases to conduct through diode and charge the battery. This also give a very interesting result in a sense that you do not have a on the DC link any ripple voltage, as far as from diode rectifier is concerned, because we will be charging from 3 sinusoidal current, and some of the 3 currents virtually at the minimum any moment of time is 0. So, that is about the simulated waveform. So, coming to a numerical solution of this problem, given that the supply voltage of 440 volt line divided by root 3 phase voltage RMS 254.03 volt and frequency of supply 50 hertz, and the DC load voltage is 580 volt, and IDC, that is the DC link current, is 60 ampere. So, the active power is like P equal to VDC IDC. So, this is something 580 into 60 watt. So, this comes 34,800 watt. The supply current, typically its RMS supply current will be this power of 34,800 watt divided by 3 into 254.03, that is the phase voltage. So, it comes the RMS current of supply with the sinusoidal waveform, of course, at unity power factor only active power flow. So, that is 45.664 ampere. The sine wave supply current after compensation results in a continuous conduction of diodes of the 3-phase bridge rectifier, E diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of diode VPH is a stepped waveform, as first step of the pi by 3 angle from 0 to pi by 3, and a magnitude of VDC by DC link voltage by 3. The second step of pi by 3 angle from pi by 3 to 2 pi by 3 and a magnitude of 2 VDC by 3, and third step of pi by 3 angle from 2 pi by 3 to pi and a magnitude of VDC by 3. It has a both half cycle of symmetric segments of such steps like. So, the RMS line voltage at the point of at the input of diode rectifier, which also called PCC, is computed as follows. The sine wave supply current after compensation results in a continuous conduction of diode of the rectifier, that is 180 degree, and it results in a quasi square wave of the AC voltage at PCC with the amplitude of DC bus voltage, and we can find out PCC RMS voltage. Typically it comes 473.57, and that is the voltage RMS voltage across the PCC line voltage. Then supply line current at unity power factor, we can calculate the supply line current, the active power drawn by the load, that is 34,800 watt divided by 3 into the phase voltage 254.03. So, it comes out 45.664 ampere. The current rating of series active power filter is that filter current, since the active filter current in series with the line, so it will be equal to line supply current equal to 45.664 ampere, since the active power filter is connected in series with the supply. The RMS voltage rating of series active filter VF is computed by taking the difference of the supply phase voltage and the phase voltage at the input of diode rectifier as follows. So, that is the RMS voltage. I mean, we can have a by half wave symmetry. So, it is a 2 by 2 pi for 180 degree we calculate. So, 0 to pi, it is the 254 into 2 peak voltage of the sine wave into sin theta, and minus, that is typically the VDC by 3 square d theta plus second segment of pi by 3 to 2 pi by 3, again the same sine wave minus 2 VDC by 3, that comes 386.67 square d theta plus last segment up to half a cycle 2 pi by 3 to pi, again sine wave of 254 into root 2 sin theta, and then VDC by 3 square d theta. And if we calculate this total RMS of which the active series active power filter is supposed to inject, it comes 81.4622 volt like. The kVA rating of VSC of APF active power filter is as S equal to 3 VF IS keeping the value 3 into 81.4622 and current 45.664 VA, it comes 11.16 kVA. So, that is the kVA rating of series active filter. Coming to the numerical problem 12, a 3-phase series active power filter consisting of voltage source converter with AC series inductor, coupling transformer and its DC bus connected to the DC bus of the load is used in series with the 3-phase supply of 415 volt 50 hertz feeding a 3-phase diode bridge rectifier with a parallel DC capacitor at a load of 60 ampere average current to reduce the harmonics in AC mains current, to maintain unity power factor of the supply current, and to regulate the DC link voltage of the load almost constant at 650 volt as shown in the figure. Calculate A RMS line voltage at the input of diode bridge rectifier, B the AC line current, C RMS current of the active series filter, D the RMS voltage across the series active filter, E VA rating of the series active filter, and F the turns ratio of the coupling transformer used in series active filter. Well, this is the total system. I mean, like here we have a again the non-linear load in which the capacitor is connected at the DC link, and then we have a series active filter. The role of series active filter here is first to maintain the sinusoidal supply current in phase with the voltage, so that it is a unity power factor, no harmonics and no reactive power on the supply. And another is that this voltage, which is a common voltage of the load and DC link, this voltage to regulate at 650 volt by appropriately injecting a suitable voltage in series with the line. So, after making a model of this whole system with the data given in the problem, the whole system is simulated, and these are the typical waveform. If we consider the supply voltage are 3-phase balance sinusoidal, then the voltage at the point of common coupling comes in this fashion, and these why we are getting this, because we are forcing the current in all the three phases sinusoidal current. So, the conduction of the diode is similar to like a 180 degree mode of operation of three phase inverter. So, whatever is the output voltage similar to of three phase voltage source inverter, similar waveform is achieved here for the phase voltage. Well, that voltage will be reflected here, and then of course, by appropriately injecting the difference of these two, that is the series active filter voltage injected here in this, we are able to achieve this three phase current, balance current, sinusoidal current in phase with the supply voltage. So, that unity power factor is achieved, and of course, the current here which is flowing towards the at the input of diode rectifier, which we can call it the AC load current, that also is the same as the source current, because both are it's a entire series circuit in that case. So, this is the voltage which we have to inject by series active filter, and it is capable of eliminating the harmonics in the supply current. Otherwise, if we do not have the series active filter in a such a voltage fed kind of load, the total harmonics distortion even most of the time is more than 60%. So, we are able to reduce from 60% even almost negligible TAD, even much less than the 5% in this case like. So, with this explanation, coming to the solution part of the numerical problem, given that the supply voltage Vs equal to 415 by root 3 and that is a 239.6 volt, frequency of supply 50 hertz, the DC link voltage is regulated 650 volt, and DC link current, I mean load current virtually drawn by the load DC load is 60 ampere. So, from this we can find out the active power drawn by the load, that is P equal to VDC IDC, that is 650 into 60 watt, that is your 39,000 watt like. The supply current IS will be 39,000 divided by 3 into the phase voltage 239.6. So, this current RMS current, which is active current only at unity power factor, it comes 54.257 ampere like. So, now coming to calculate the virtually the voltage, I mean like of series injection, that I mean we have to go the supply sine wave supply current after the compensation results in a continuous conduction of diode of the three phase diode rectifier, which is a part of the load. So, each diode conducting for 180 degree, and it results in a waveform of the phase voltage at the input of diode VPCH is a stepped waveform as first segment or step of pi by 3 angle from 0 to pi by 3 and a magnitude of VDC by 3, and second segment of pi by 3 angle from pi by 3 to 2 pi by 3 and a magnitude of 2 VDC by 3, and third step of pi by 3 angle from 2 pi by 3 to pi and a magnitude of VDC by 3, and it has a both half cycle of symmetric segment of such steps. So, the RMS line voltage at the input of diode rectifier is computed from that waveform which is shown in the previous figure. So, sine wave supply current after compensation results in continuous conduction of diode, that is 180 degree, and it results in a Cauchy square waveform, the PCC with the amplitude of DC voltage, I mean so it comes 530.72, and that is the voltage RMS voltage at the point of common coupling or input of diode rectifier. So, the supply current, I mean line current at unity power factor is your active power drawn by the load, that is 39,000 watt divided by 3 into the phase voltage, because power factor is maintained unity, it comes to 39.6 volt. So, the net current comes 54.257 ampere like, and the current rating of series active filter is the same as the filter current is equal to supply current, because both are connected in series, and that is 54.257 since active filter series active filter is connected in series with the supply like. So, the RMS voltage rating of series active filter VF is computed by taking the difference of the supply phase voltage and the phase voltage at the input of diode rectifier as follows. So, this is the RMS voltage, I mean since that waveform will be a symmetric about half cycle. So, we can take like 2 upon 2 pi. So, we can take only for half cycle 0 to pi by 3 of sine wave of 239 to root 2 p minus the VDC by 3, I mean that is 261.67 square. Then the second segment of pi by 3 to 2 pi by 3 with the sine wave minus 2 VDC by 3, and plus the third segment 2 by 3 to pi, and it comes like again sine wave with the VDC by 3 square, and taking RMS value, putting all these, doing the calculation, it comes 105.27 volt. So, that is the voltage we have to inject RMS voltage in series with the line by series active filter. and the kV rating of APF active series active filter is S equal to 3 VFIS, and it will be 3 into 105.27 into 54.257. So, if we calculate all, it comes 17.135 kVA. Now, the turns ratio of the coupling transformer is computed as what the maximum voltage AC voltage on AC side of this voltage source filter of series active filter can generate by this relation, that comes 183.85, and the supply side it must be Vf, which we have calculated for series active filter. The turns ratio of coupling transformer can be calculated, the voltage on VSI and voltage to be injected on turns on the supply side. So, the inverter is capable of generating 183.85 volt, and the injected on supply side is 105.27. So, turns ratio comes 1.746 like. So, coming to the 13th example, a series active power filter consisting of voltage source converter with AC series network coupling transformer and its DC bus connected to DC bus of the load is used to reduce the harmonics in AC mains current and to maintain almost unity power factor connected in the series of the 3-phase AC supply or 415 volt 50 Hz feeding a 3-phase diode rectifier with a capacitive filter of 10,000 microfarad and a resistive load of 20 ohm as shown in the figure. So, DC bus voltage of the load is decided to result in a minimum injected voltage of series active filter. Calculate A, RMS voltage at the input of diode rectifier, B, the line current, C, the VA rating of the series active filter, D, the DC link voltage of the load, and E, the turns ratio of coupling transformer. So, this is the typical circuit of course of this series active filter. We have a non-linear load with the capacitive, the DC link is common with the series active filter, and we have to, of course, series active filter have to inject voltage in such a manner that we force all the 3 phases to conduct all the 3 diodes in a manner, and these current become the sinusoidal in phase with the supply voltage. So, that supply side behave like a unity power factor and another job is that this series active filter have to regulate this load voltage, typically with again appropriate injection of the voltage, in a manner that this voltage in such a manner that this voltage what we reflected on AC side and the difference of this the injected voltage in this series is minimum. So, that the series active filter rating will be minimum like. So, in that case we have to after making the complete design and model of it, with the data given in the problem, the waveforms are simulated and these are the simulated waveform. 3-phase supply voltage which is balanced sinusoidal, and the voltage at the input diode rectifier because of the conduction of all 3 phases, per phase voltage is reflected at the input of diode rectifier, and if we inject the difference of these two, that is the series active filter voltage to be injected series with the line, then we will get of course the supply current balanced sinusoidal in phase with the voltage, and then same will be the current which is flowing typically on the input of diode rectifier. The one important aspect which is asked here in the problem, that this voltage injected should be minimum in the sense that this voltage should be enhanced, DC link voltage should be enhanced in such a manner that the injected voltage is minimum. So, that comes to be a quite interesting problem coming to the numerical part of this, giving that the supply voltage Vs equal to per phase voltage 415 by root 3, that is 239.6 volt, and frequency of supply 50 hertz and the load resistance is 20 ohm. So, if we consider x volt is the DC link voltage of the rectifier load, then the injected voltage of the APF is calculated typically in terms of x. So, that is virtually again typically 3 segments because it is symmetric about the 180 degree half cycle. So, it becomes like 2 upon 2 pi, first segment 0 to pi by 3 Vs into root 2 sin theta minus x by 3 square plus second segment pi by 2 2 pi by 3 again Vs into root 2 sin theta minus 2x by 3 and square and d theta, and third segment 2 pi by 3 theta again V s into root 2 sin theta minus x by 3 square d theta. So, now like virtually we can say that is x is the DC link voltage. So, we can find out for minimizing the Vf, the typically you can call it the value of x. So, after integrating and taking the derivative with respect to x, it gives the x value corresponding to this here, and that comes typically 485.36 volt like. So, now I mean once we know the DC link voltage, we can find out the DC load current, because we know the resistance of the DC load current. So, it becomes like VDC by RDC, and that is 485.36 divided by 20, it comes 24.268 ampere like. And now we can calculate the active power, because it will be equal to P equal to VDC IDC. So, we already got the value of VDC 485.36 into 24.268. So, it comes like 11,778.747 watt like. Now, we can find out the supply current, because we got the active power consumed by the load 11,778.747 divided by 3 and into 239.6, and power factor unity on the supply. Current is maintained sinusoidal balance current at in phase with the supply voltage, so power factor unity, and it comes 16.39 ampere line. Now, coming to the actual calculated, typically the sine wave supply current after the compensation results in a continuous conduction of diode of 3-phase rectifier, each diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of diode VPCC as a step waveform, as a first step of pi by 3 angle from 0 to pi by 3, and a magnitude of VDC by 3, second step of pi by 3 angle from pi by 3 to 2 pi by 3, and a magnitude of 2 VDC by 3, and the third step of pi by 3 angle from 2 pi by 3 to pi, and the magnitude of VDC by 3, and it has a both half cycle of symmetric segment of such step. So, the RMS line voltage at the input of diode rectifier is computed as the sine wave supply current after compensation results in a continuous conduction of diode rectifier 180 degree, and it results in quasi square wave of AC voltage at PCC with the amplitude of DC bus voltage VPCC equal to VDC into root 2 by 3, it comes 396.29 volt. So, PCC RMS voltage 396.29 volt, and the supply current at unity power factor is the same as we calculated supply current 16.39 ampere, and the current rating of series active filter is the same as filter current equal to supply current, because they are connected in series with the line, and it is 16.39 ampere, since series active filter is connected with the series with the supply. And the RMS voltage rating of series active filter VH computed by taking the difference of the supply phase voltage and the phase voltage at the input of diode rectifier by VF equal to taking a 3 segments, because it is symmetric about the half cycle. So, we can take only half cycle. So, it comes to 2 by 2 pi. So, that comes 1 upon pi. So, it is a 0 to pi by 3, and sine wave of 239.6 into root 2 sin theta minus the VDC what we calculated by 3 square d theta, second segment pi by 2 to 2 pi by 3, again the sine wave of 239.6 into root 2 sin theta minus 2 VDC by 3, that is a 323.57 in square into d theta plus the third segment 2 pi by 3 to pi, and say 239.6 into root 2 sin theta minus VDC by 3, that comes 161.79 square d theta. So, after keeping the value of all and solving it, it comes 71.12 volt like. Now, the kVA rating of the voltage source converter of series active filter is S equal to 3 VF IS, it comes 3 into 71.12 the voltage we calculated, and the current is the same as supply current 16.39. So, the rating comes 3.497 kVA like. And the turns ratio of the coupling transformer of series active filter is computed. The maximum AC voltage of AC side of voltage source converter of APF may be generated by MA VDC by 2223, and taking MA equal to 0.8, it comes 137.28, and on the supplied side it is just injected voltage. So, that we have already calculated. So, we can find out the turns ratio on the inverter side turns, and then the supply side turns where we are injecting, putting the value on both sides the voltage, the turns ratio comes 1.93 or so. So, coming to the problem number 14 solved problem, a series active power filter consisting of voltage source converter with AC series inductor, coupling transformer, and its DC connected to the DC bus of the load is used to reduce the harmonics in AC mains current and to maintain the almost unity power factor in series with the 3 phase AC supply of 400 volt 50 hertz, feeding a 3 phase diode rectifier with a capacitive filter of 40,000 microfarad and resistive load of 10 ampere as shown in the figure. If the DC bus voltage of the load is to be maintained constant ripple free of 600 volt, then calculate the RMS line voltage at the input of diode rectifier, AC line current, RMS current of the series active filter, RMS voltage across the series active filter, volt ampere rating of the series active filter and the turns ratio of coupling transformer. So, in the circuit here also we have a common DC bus of the load and series active filter, and we inject the appropriate voltage in a manner that these currents are in phase with the supply voltage at unity power factor and they are harmonics free balanced sinusoidal current. That is possible only by injecting appropriate voltage and forcing this current to flow in all the 3 phases, and this capacitor or the power is fed to the load with the sine wave current through diode rectifier. So, since we are forcing this all the diodes to conduct all the 3 phases, certainly the voltage of DC link get reflected on this AC side. So, after making the complete model of this system with the data given in the column, the whole system is simulated and these are the waveform which we got it. If we consider 3 phase supply voltage sinusoidal balance, then this is the voltage typically comes here after the injection of this voltage by series active filter. So, if we inject this voltage, the difference of this voltage automatically will be of this nature, and if we really enforce such condition, then we get the supply current balance sinusoidal and in phase with the supply voltage having a unity power factor. And of course, the whatever the supply current is the input of AC side of your load current, because they are connected in series . So, coming to solution part of this with the numerical portion, given that the supply voltage is 400 by root 3, that is 230.94 volt, and frequency of the supply 50 hertz, DC link voltage is VDC equal to 600 volt and the load resistance at DC link is 10 ohm, and DC load current edge is VDC by RDC. So, it comes your 600 volt by 10 ohm, so it comes 60 ampere, and the active power which is load is drawing P equal to VDC IDC is a 600 into 60. So, that comes 36,000 watt or 36 kilowatt. Now, we can calculate the supply current which is series active filter current also. I is equal to 36,000 divided by 3 into 230.94. So, it comes like a 51.96 ampere . And now, coming to calculate the series injected voltage, the sine wave supply current after the compensation results in a continuous conduction of diode of the 3 phase diode rectifier, E diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of diode is a stepped waveform. First step is of pi by 3 angle from 0 to pi by 3 and a magnitude of VDC by 3. Second step of pi by 3 angle from pi by 3 to 2 pi by 3 and a magnitude of 2 VDC by 3, and third step of again pi by 3 angle from 2 pi by 3 to pi and a magnitude of VDC by 3, and it has a both half cycle of symmetric segment of such steps. The RMS line voltage at the input of diode rectifier is computed as follows. So, sine wave supply current after the compensation results in a continuous conduction of diode of the rectifier, and it results in quasi square wave AC voltage at PCC with the amplitude of DC bus voltage PCC equal to VDC into root 2 by 3. So, it comes 489.89. Therefore, PCC RMS voltage is at the input of diode rectifier 489.89. The supply line current at unity power factor, that is even IS equal to power, active power drawn by the load, that is 36,000 watt divided by 3 into phase voltage, because power factor is unity, that is come 51.96 ampere, and the current rating of the series active filter is the same IF equal to IS, because this filter is connected in series with the line. So, it is also same as 51.96 series active power filter, because since is connected in series with the line. And the RMS voltage rating of the series active filter VF is computed by taking the difference of the supply phase voltage and the phase voltage at the input of diode rectifier as follows. So, we have VF as a 3 segment again of half wave symmetry of 2 by 2 by 3. So, we will calculate only for 180 degree 0 to pi by 3, the sine wave of 239.94 into root 2 minus VDC by 3, that is 600 by 3 means 200 square into d theta. Second segment pi by 2 by 3, and again sine wave of 230.94 into root 2 sin theta minus 2 VDC by the, that is 400 square d theta, plus the third segment 2 pi by 3 pi, that is 230.94 into root 2 sin theta minus VDC by 3, that is 200 square d theta. So, it comes like a 92.6382 volt like, and the kV rating of voltage source converter of series active filter is now S equal to 3 VF IS. So, it is a 3 into, I mean VF we are calculating here 92.6382 multiplied the current, I mean which is down from supply and series active filter is connected in series. So, that is the same current 51.96 VA. So, it comes 14.44 kVA is the rating of the series active filter, and the turns ratio of coupling transformer is computed as, so the maximum voltage AC voltage on the AC side of voltage source converter of active filter may be by this relation MA VDC by 2 root 2. So, putting the value of MA equal to 0.8, it comes 169.7 volt, and on the supply side it injects equal to VF. So, turns ratio of the coupling transformer is your typically turns on voltage source inverter side divided by turns on supply side which we are injecting. So, this is the voltage inverter can generate 169.7 volt, and this is the voltage which have to inject on the into the supply. So, this is 92.6382. So, the turns ratio comes 1.83 or so. So, coming to the numerical problem 15, a 3-phase series active power filter consisting of voltage source converter with AC series inductor, coupling transformer and DC bus capacitor is used to in series with the 3-phase AC supply of 415 volt 50 hertz, feeding a 3-phase 12 pulse diode rectifier consisting 2 parallel connected 6 pulse diode bridge rectifier with the star delta and star and delta delta transformer to output equal to the line voltage of 415 volt, having the parallel DC capacitors filter with 500 volt 400 volt DC at the at a load of 60 volt average current, 60 ampere average current to reduce the harmonics in the AC mains current and to maintain the unity power factor of supply current as shown in the figure. Calculate A, the RMS phase voltage at the input of 12 pulse diode rectifier, B, the AC line current, C, the RMS current of the active series filter, and D, the RMS voltage across the active power filter, the V rating of active power filter. So, these are typical circuit. I mean here we have a load which is a 12 pulse converter, isolate converter, star delta, delta delta, and both converter are connected in parallel with the capacitive load, and that is the voltage and load is given. So, now in this case if we put a injection of this voltage with series active power filter, and typically we can by appropriate injection of the voltage we can maintain these line current, supply line current balanced sinusoidal at unity power factor in phase with the voltage, and the injected voltage, now the input voltage will be like kind of a step waveform, I mean like form when we are forcing all the 3 phases, this will look like a typically a voltage of like a similar to like a 12 pulse converter. So, you can call it like here if you after making the complete model of it and putting the data of the problems, this whole system is simulated, and these are the supply voltage. This is the voltage at the input of typically of this diode rectifier, which is the voltage you can clearly see like a 12 pulse converter voltage, and if we inject the difference of these two this and this, we will be able to have the all 3 phase current balanced sinusoidal and in phase with the voltage. So, this is the typically supply current, and this is the current here at the input of diode rectifier, both current are same because it is a series connected. So, this is the voltage we have to inject in case of this typical non-linear load of 12 pulse converter also. Now, coming to the solution part of it, given that the supply voltage is 415 by root 3 and that is 239.6 volt, we can say 50 hertz, and the DC link voltage is 400 volt and the DC link current is 60 ampere. The active power drawn by the load will be P equal to VDC IDC, that is 400 into 60 watt, that is 24,000 watt or 24 kilowatt, and the supply current is estimated as, that is active power 24,000 watt divided by 3 into 239.6 volt. So, it comes 33.389 ampere like. So, coming to the sine wave supply current after the compensation results in a continuous conduction of diode of the 3-phase diode rectifier, E diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of 12 pulse diode rectifier. We see in a stepped waveform, a first step of pi by 6 angle from 0 to pi by 6 and a magnitude of VDC in bracket 2 by root 3 minus 1. Second step of pi by 6 30 degree, pi by 6 to pi by 3, and a magnitude of VDC 1 minus 1 by root 3, and the third step of pi by 6 angle from pi by 3 to pi by 2, and a magnitude of VDC by root 3, and it has a all 4 symmetric segment of such a step in remaining half cycle, remaining 90 degree of half cycle line. So, the turns ratio now the turns ratio of the transformer is calculated at typically the voltage what we can get, that is from 400 volt, the line voltage we can generate 296.19 and the primary side is 415. So, we can find out the turns ratio of the star delta transformer root 3 to 0.8, typically 81, and the primary to secondary turns ratio of the delta transformer typically of the load, I mean we can just calculate from this come 1.1, hence the turns ratio 1.4 is to be multiplied with each step. So, RMS phase voltage at the input of 12 pulse diode rectifier is computed as from this relation, that comes 1.4 VDC under root 1 by 2 upon 2 pi or 1 by pi, and taking a segment only for typically of half cycle. So, 0 to pi by 6, I mean this is the typical segment in terms of VDC, that is the second segment, this is the third segment, this is the fourth segment, this is the fifth segment, and that give you the voltage, I mean RMS voltage at PCC equal to 236.8 volt, and the supply line current at unity power factor is your IS equal to active power 24,000 divided by 3 into 239.6 equal to 33.389 ampere like, and the current rating of the series active filter is the same IF equal to IS equal to 33.89 because this is connected in series with the line. So, both current are same like. So, RMS voltage rating of the series active filter, now we can find out from this relation typically of a 5 segment 2 upon 2 pi. So, first segment of 0 to pi by 6 30 degree sine wave of this minus the voltage in terms of VDC which we have calculated earlier. The second segment 239 again in terms of DC link voltage VDC 1 minus root 3. Similarly, third segment, fourth segment and fifth segment. There are fifth segment in the voltage even in one half cycle that waveform. So, after calculating and putting the value, it comes to 36 volt, and the now kVA rating of series active filter is S equal to 3 VFI IS. So, it is a 3 into 36 into 33.389. So, it comes 3.606 kVA rating. Why this rating is less than the 6 pulse converter? Because here we have a less harmonics typically to be injected in the system, because it is already 12 pulse converter or so. And now coming to the 16th numerical problem, a 3-phase series active power filter consisting of voltage source converter with the AC series inductor, coupling transformer and DC bus connected to the DC link of the load is used in series with the 3-phase AC supply of 440 volt 50 hertz feeding a 3-phase 12 pulse diode rectifier consisting of 2 parallel connected 6 pulse diode bridge rectifier with the star delta and delta delta transformer to the output equal to the line voltage of 440 volt, having a parallel DC capacitor of 10,000 microfarad with a 20 ohm resistive load DC to reduce the harmonics in the AC mains current and to maintain the unity power factor of the supply current as shown in the figure. If DC bus of the load is to be regulated to 650 volt, then calculate the RMS phase voltage of 12 pulse diode rectifier, the AC line current, and see the RMS current rating of the series active filter, D the RMS voltage rating of the series active filter, and E the VA rating of series active filter, and F the turns ratio of the coupling transformer. So, this is the typical circuit. I mean we have here 12 pulse converter, voltage fed load because capacitor is connected at the output, and we have a series active filter I mean here, and we have a supply. So, this series active filter have to inject typically the voltage in such a manner that these current become sinusoidal balance and in phase with the voltage. So, that is unity power factor is achieved. So, after making a complete model of this system and simulating it, so the behavior comes in that way. This is the input supply voltage, this is the voltage at the input of diode rectifier at this point, step waveform, and the difference of these two we inject with the help of series active filter here then we are able to get 3 phase balance supply current in phase with the supply voltage on supply side, and this is the current of course at the input of diode rectifier. Since circuit is series, so both current will be the same. So, coming to the calculation part of this, typically of the solution of this problem, given that supply voltage of 440 by root 3, that is 254 volt, frequency of supply 50 Hz, VDC 650 volt and RDC 20 ohm, the DC load current will be your VDC by RDC. So, that will be your 650 by 20 means 32.5 ampere, and the active power now drawn by the load will be P equal to VDC IDC, that will be 650 into 32.5 watt, that is 21,125 watt, that is the active power load is drawing. Now, we can find out the supply current from this, that is Is equal to active power divided by 3 into phase voltage on the supply side, and power factor is maintained unity. So, it comes like a 27.72 ampere. So, now coming to calculate the typically the your voltage at the PCC as well as the series active voltage. So, sine wave supply current after the compensation results in a continuous conduction of diode of the 3 phase diode bridge rectifier, and each diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of 12 pulse rectifier. EPCC is a step waveform, a first step of pi by 6 angle 0 to pi by 6, and magnitude of VDC in bracket 2 by root 3 minus 1, second step of pi by 6 angle from pi by 6 to pi by 3, and a magnitude of VDC 1 minus 1 by root 3, and the third step of pi by 6 angle from pi by 3 to pi by 2, and a magnitude of VDC by root 3, and it has a all 4 symmetrical segment of such nature because it is only for 90 degree. And the turns ratio of the transformer can be calculated because we know the typically now in terms of line voltage, this is the DC link voltage. So, we can find out line voltage 481.312 RMS, and the supply side primary side is 440 volt. So, we can find out the primary to secondary turns ratio of the star delta transformer from this primary and secondary voltage. So, it comes 0.528, and the primary to secondary turns ratio of delta delta second transformer, it will be this voltage. So, it is 0.914, and hence the turns ratio of 0.914 will be multiplied with each step. So, RMS phase voltage at the input of 12 pulse converter is calculated from this relation. This is the voltage what we are calculating at the virtually a segment of your stepped waveform at the diode rectifier input. So, 0.914 VDC 1 upon pi. So, first segment, second segment, third, fourth and fifth segment, and this voltage comes at the RMS voltage at the input of diode rectifier 251.1 volt, and the RMS supply line current at unity power factor is Is equal to the active power 21,125 divided by 3 into the phase voltage at supply 254, because power factor is unity. So, it comes 27.72 ampere, and the line and the current rating of series active filter is as Is equal to 27.72, since active power filter is connected in series with the supply, and the RMS voltage rating of the series active filter we calculate here again from the 5 segment of difference between sine wave and the step wave, which we have already discussed 2 upon 2 pi. So, first segment of 30 degree, second segment of 30 degree, fourth segment 30 degree, fifth segment and 50. So, with this calculating this, it comes only 38.22 volt. We already discussed that this is lesser than the previous what 6 pulse converter. In 12 pulse converter you have a less harmonics in that, and the input voltage of diode rectifier is also closer to sine wave, and the kV rating of the VSC voltage source converter of active filter is 3 into VFIS. So, it is a 3 into the voltage injected, which we calculate 38.22 into the current 27.72. So, it comes 3.18 kVA, and the turns ratio of the coupling transformer of the series active filter is as follows. The maximum AC voltage on the AC side of voltage source converter of active power filter may be by MA VDC by root 2. So, it comes 183.85, and on the supply side we have to inject only the voltage which is required by series active filter. So, turns ratio of the coupling transformer will be your inverter side virtually turns, supply side. So, both side of voltage it comes 4.81. So, coming to the numerical problem 17, a 3-phase series active power filter consisting of voltage source converter with AC series inductor and its DC bus connected to the battery behaving as a load is connected in series with the 3-phase AC supply of 415 volt 50 Hz, feeding a 3-phase 12 pulse diode rectifier consisting of two parallel connected 6 pulse diode rectifier with a star delta and delta delta transformer to output equal line voltage of 415 volt, charging a battery of 500 volt at a 100 ampere average current DC current as is shown in the figure. So, series active filter is employed to reduce the harmonics in AC mains current and to maintain the almost unity power factor of the supply current. Calculate A, the RMS phase voltage at the input of 12 pulse diode rectifier, B, the AC line current, C, the RMS current of series active filter, the D, RMS voltage across the active filter, E, the VA rating of the active series active filter, F, the turns ratio of the coupling transformer. So, this is the typical circuit here. I mean, here also the battery is not always only connected across the load, but it is also connected to the in series with the series active filter on the DC link, and DC link is common, and we are injecting with the help of series active filter in a voltage in a manner that these current become sinusoidal as well as in balance and in phase with the voltage. So, that power factor unity and harmonics are also due. I mean, so virtually here series active filter is working to eliminate the current harmonics like. So, after making the model of complete system, and putting the data given in the problem, the its simulated waveform are here 3 phase voltage, and the voltage at the input here at the input of diode rectifier comes this, and the difference of this we inject this voltage by series active filter here. So, the typically the currents come 3 phase balance current, sinusoidal current in phase with the voltage. You can just look into, and this is virtually the current at the input side. So, since circuit is series, so both current will be the same. So, coming to a numerical part of this solution, given that the supply voltage is Vs equal to 415 by root 3, that is 239.6 volt, and frequency of supply 50 hertz, and DC link voltage 500 volt, and the DC link current is 100 ampere. So, we can calculate the active power drawn from the supply P equal to VDC IDC, that is 500 into 100. So, it comes 50 kilowatt or 50,000 watt, and supply current as we can calculate from power divided by 3 into phase voltage 239.6 and power factor is unity. So, it comes 69.56 ampere like. So, now coming to calculate the typically the input RMS voltage of the diode rectifier, the sine wave supply current after the compensation results in a continuous conduction of diode of the 3 phase diode rectifier, E diode conducting for 180 degree, and it results in the waveform of the phase voltage at the input of 12 pulse diode rectifier is a stepped waveform of a first step of 30 degree pi by 6 angle from 0 to pi by 6, and a magnitude of VDC in bracket 2 by 3 root 3 minus 1, and second step of pi by 6 angle from pi by 6 to pi by 3, and a magnitude of VDC 1 minus 1 by root 3, and the third step of pi by 6 angle from pi by 3 to pi by 2 and magnitude of VDC by 3, and it has all 4 symmetric segment of such nature. It is only for 90 degree, remaining 90 is the replica and 180 is the further replica. So, the turns ratio of the transformer used in the load we can calculate from this, that is rectified voltage equal to 500. So, we can find out input line voltage is 370.24 and primary is 475. So, we can have a primary to secondary turns ratio of star delta transformer. So, primary turns, secondary turns from this voltage it comes 0.647, and the primary secondary turns of delta delta connected transformer, putting the voltage on both sides, we get the turns ratio 1.121. Hence, the turns ratio of 1 to 1 will be multiplied with the each step, and the RMS phase voltage at the input of 12 pulse diode rectifier is computed as again the segment 1.21 1 to 1 VDC, and that is the first segment. It is a 2 upon 2 pi, so it comes half wave only. So, first segment, second segment, third, fourth, fifth segment total. So, from this we can calculate the RMS voltage at the input of diode rectifier comes 236.87 volt like, and the supply line current at unity power factor is your IS equal to 50 power active power divided by 3 into your phase voltage 239.6 and power factor is unity. So, this comes the supply RMS current, so it comes 69.56, and the current rating of series active filter is IF equal to IS, that is 69.56 ampere, since active power filter is connected in series with the supply. And the RMS voltage rating of the series active filter is calculated again here 2 upon 2 pi. The first segment sine wave minus the reflected voltage from the diode rectifier input, then the second segment again sine wave, second segment, third segment, fourth segment or 5 segment. So, there are typically kind of 5 segments, and from this we are calculating this voltage comes 36 volt, and the kV rating of the VSC of active filter is your 3 VFIS equal to 3 into VF 36 and current 69.56, it comes 7.5 kVA. And the turns ratio of the coupling transformer used in series active filter, we can calculate the maximum AC voltage on AC side of active power filter is from this relation. It comes 141.42 volt, and on the supply side it must inject only VF. The turns ratio comes from inverter side turns and the supply side turns. So, it comes 141.42 divided by 36. So, it comes 3.92 or so. So, coming to the problem number 18, in a 3-phase line voltage of 380 volt 50 hertz 4-wire distribution system, 3 single phase loads connected between phase and neutral, having a set of single phase uncontrolled diode with reactive converter which have a RE load of R equal to 10 ohm and E equal to 220 volt. As shown in the figure, it is desired to charge the battery E with average current of 15 ampere. Calculate the supply phase current if 3-phase series active filter consisting of VSC with series active inductor coupling transformer and DC bus connected DC bus capacitor is connected in series with the 3-phase supply lines to maintain unity power factor at DC mains. Calculate the A supply current, B RMS current of the series active filter, C the RMS voltage of the input of rectifier, and D the RMS voltage of the voltage across the series active filter, and E the VA rating of the series and D the neutral current. So, this is the system. We have a 3-phase 4-wire system. So, we have a load diode rectifier with the typically RE load. We are charging the battery and all 3 are symmetrical in nature. So, such load will certainly cause the, typically you can call it the excessive neutral current if series active filter are not connected. So, we are connecting series active filter, and by making a complete model and putting the, and the very purpose that we must have a sinusoidal current, balance current, sinusoidal current in phase with the phase voltage, and the neutral currents will be eliminated automatically. So, making a complete model of this system and putting the value which is given in the problem, we are able to get the waveform. This is the 3-phase supply voltage at the input. This is the voltage at the diode rectifier input for each phase, which is like very close to the kind of a square wave. And if we inject this voltage, the difference of these two virtually by series active filter of this voltage we inject, then we will get of course this current balance sinusoidal and in phase with the supply voltage, and this current is supply current, this is the current on the input of the load. So, both are connected in series, so it will be the same. It is only that we inject this voltage only, then this condition will be there. So, coming to a numerical part of it, if we could not have used this, then there could have been excessive neutral current is flowing like in that case, and we might have a very peaky current, drawing the current only for very short period depending upon the voltage magnitude of the your load or so. So, solution, given that the voltage phase voltage is line voltage 380 by root 3 to 19.39 and frequency 50 hertz, a load of 10 ohm, and typically the DC voltage 220 volt, and it comes typically of your IDC equal to come of 15 ampere. So, since a series active filter is used to make the supply current sinusoidal, the RMS supply current corresponding to average current of IDC will be from RMS current on the supply side will be corresponding to 16.661 ampere, and the active power will be 3 ISC square R plus EDC. So, that is the putting the value, we get the active power of all 3 phases, it is 18,227.479, and from this we can calculate the supply current. From this which we have calculated, so it comes typically 16.661 ampere, and the current rating of the series active filter is also the same as 16.661 ampere. So, supply RMS voltage of the diode rectifier is from P, we can calculate because diode is conducting continuously, it comes from the same voltage as a battery voltage plus the resistance drop. So, it comes 275.969, and the voltage rating of the series active filter is your typically is calculated again sine wave minus the difference of your in the segment, like typically coming out from the your rectifier, and from this putting the value on both sides. So, it comes 175.4.004 volt, and the VA rating of series active filter 3 into VFIS. So, putting the value it comes 8.697 kVA, and since all the 3 phase currents are sinusoidal and balanced, the neutral current of supply is 0. So, coming to the 19th problem, in a 3-phase line voltage of 415 volt 50 hertz 4-wire distribution system, 3 single phase load connected between the phase and neutral having a set of single phase uncontrolled diode bridge direct converter which have a RE load equal to R equal to 2 ohm and battery voltage 264 as shown in the figure. It is desired to charge the battery with the average current of 15 ampere. If the 3-phase series active power filter single phase voltage source converter with the AC series inductor coupling transformer and DC bus is connected to the battery is connected in series with the 3-phase supply line to maintain the unity power factor at AC means calculate A AC line current, B the RMS current of the APF, C the RMS phase voltage at the input of diode rectifier, D the RMS voltage across the APF and the VA rating of APF, and F is the turns ratio of coupling transformer. So, this is the typical circuit. We have a 3-phase 4-wire system, we have resistance, we have a battery, we have a current flowing on this side. Okay. So, that is a highly nonlinear load. If we do not connect series active filter, you have excessive neutral current and virtually you will have a even typically the very highly nonlinear current in the supply also. But after putting series active filter and injecting a right voltage, we are able to get the 3-phase current sinusoidal balance at unity power factor, then neutral current is made 0 pi. So, after making a complete model of this system and simulating it with the data given in the column, we are able to get like a 3-phase voltage. This is the voltage at the input of diode rectifier and this is the current on the supply side which is balanced sinusoidal in phase with the supply voltage, and this is the current on the diode side, both are connected in series same current, and this is the injected voltage by this series active filter. So, if this voltage is injected, then only your current will become sinusoidal balance and unity power factor. So, coming to numerical portion of it, given that supply phase voltage is Vs equal to 415 by root 3 to 39.6 volt, frequency of supply 50 hertz and a load of R equal to 2 ohm and battery voltage is 264 volt and the DC side current is given average current 15 ampere. So, since series active filter is used to make the supply current sinusoidal in each phase, so RMS supply current corresponding to the average current of IDC will be equal to pi DC upon root 2. So, it becomes 16.667 ampere and the active power will be typically 3 ISC square loss in resistance plus the your battery charging power. So, putting the value of this, so it comes like a 13,545 watt and the RMS supply current at unity power factor will be what we calculate here 16.66 ampere and the RMS current rating of the series active power filter also will be 16.66 ampere. So, coming to the RMS voltage at the input of diode rectifier will be this E square plus ISC square this, so it comes to 66.09 and the voltage rating of the series active filter will be now calculated from the supply voltage voltage for the half symmetry and minus the typically the voltage reflected from diode rectifier and typically this is the voltage reflected from diode rectifier square and taking this putting the value of this, it comes typically like your 119.1164 volt and the VA rating of series active filter is 3 into VFIS. So, putting the value of this, it comes 5953.4 VA and the turns ratio of the coupling transformer is calculated. The maximum voltage on AC side of voltage source converter of APF is MA this. So, this is the voltage 74.67 volt and on the supply side we have to inject only the active power filter voltage. So, turns on inverter side, turns on supply side, this is the voltage on inverter side, this is the voltage what we want to inject. So, it comes turns ratio 0.6268. So, coming to the sole example of 20 in the 3-phase line voltage of 380 volt 50 hertz 4-wire distribution system, 3 single phase load connected between phase and neutral having a set of single phase uncontrolled diode bridge direct converter which has a resistive load R equal to 10 ohm and parallel capacitive filter of 1000 microfarad. It is desired to maintain DC bus voltage of 200 volt. If the 3-phase series active filter 3 single phase VSC with the AC series inductor coupling transformer and its DC bus connected to a capacitor is connected in series with the 3-phase supply line to eliminate neutral current and to maintain unity power factor at the AC mains, calculate A the AC mains line current, B the RMS current of the active filter, C the RMS phase voltage at the input of diode rectifier and D the RMS voltage across the active power filter and the VA rating of active filter E and F is the turns ratio of coupling transformer. So, this is the typical circuit of the if we do not use the active filter will be highly distorted current conduction of very short time, and if you put series active filter, these current will balance sinusoidal in phase with the voltage, so neutral current will be eliminated. And by injecting appropriate voltage, we can have this input diode voltage typically, supply voltage is this. So, input of diode rectifier will be of this nature, which will be reflected, and the difference of these two we are injecting here. You can see the voltage, this is series injected voltage, and after injecting this we are getting this supply current balance sinusoidal in phase with the voltage. So, unity power factor on supply, since it is connected, this is the input of diode rectifier, that current will be also sinusoidal current like. So, coming to solution part of it, given that supply phase voltage equal to Vs equal to 380 by root 3, that is 219.39 volt, frequency of supply 50 hertz, and a load of 10 ohm with the DC link voltage of 200 volt. So, we can find out the DC load current, that is DC link voltage divided by load resistance, that is 20 ohm ampere. And since a series active filter is used to make the supply current sinusoidal in each phase, the RMS supply current corresponding to this will be your typically you can call it like your power divided by the voltage of supply per phase. So, it comes 18.23 ampere, and the power active power 3 VDC IDC total power. So, it will be your 12,000 watt 12 kilowatt, and the RMS supply current at 18.23 ampere, and the supply typically RMS current of rating of series active filter is the same as the supply current. So, it is 18.23 ampere. So, the sine wave supply current after the compensation results in a continuous conduction of diode of the rectifier 180 degree, and the results in a square wave at PCC with amplitude of DC bus voltage of 200 volt. Therefore, PCC voltage 200 volt, and voltage rating of series active filter will be virtually the sine wave minus the DC bus square. So, it comes 95.52 volt, and the series active filter rating is your 3 into VFIF. So, putting the value, it comes virtually, you can call it like a 5.22 kVA like. So, this we have to keep of 95 point something, and then the current rate here like. So, it comes 5.22 kVA, and the turns rates of the coupling transformer is computed as maximum AC voltage of APF is, this is the inverter can generate it 50, and what the on supply side we need VF. So, turns ratio from PSI side and supply side turns, that comes the voltage on both sides, it comes 0.5292 like. Well, we like to summarize now. This series active filter are used to compensate the voltage quality problems of the supply system. They protect sensitive load from interruption, which causes loss of production and maloperation of the other critical equipment such as medical and healthcare system. And the series active power filter are also used to compensate the power quality problems of harmonic currents of voltage fed kind of load, of non-linear load, by injecting the appropriate voltage to block the harmonic current, like which we have given many examples. And these series active filter offer the best solution for voltage fed non-linear load with moderate rating. The pendulum based voltage source converters are preferred to realize the series active power filter because of low cost, reduced size, light in weight, and reduced losses. An analytical study of various performance indices of series active filters for compensation of voltage based power quality problem of different types of load and the harmonic current compensation of voltage fed kind of load is made in detail with the several numerical examples to study the rating of power filters and how it is affect the nature of various kind of non-linear load. And series active filters are also observed one of the best retrofit solution for mitigating voltage power quality problem across various type of load and harmonic currents of voltage fed kind of non-linear load for reducing the pollution of AC mains current. And these are the references like for this topic, and thank you very much like.